I think that should be recording the microphone and any questions. And so we can get right into it. So this is just the second session, and we're going to be going over section 1.1, which is just kind of the foundations of infinity category theory. And so just as like a quick little review, we've kind of mentioned the fundamental n-groupoid, which has morphisms up to n, all of which are invertible. And this is the homotopy theory viewpoint, where our higher morphisms are higher homotopies. An NR category, then, is going to be having k morphisms for up to k equals n, in all of the k morphisms for k above r are invertible. And we call infinity zero categories, where everything's invertible, to be infinity groupoids. And infinity one categories, we're also just going to call infinity categories. And so we can try and define these from our homotopy theory viewpoint as a category enriched over a nice category of spaces. And for this, we're going to choose compactly generated Hausdorff spaces. And we do composition by just taking continuous maps. But this definition is not really good to work with. It ends up being really difficult to actually prove anything about it. So instead, we want to approach this using quasi-categories, which are going to be certain simplicial sets. These still kind of have a homotopy theoretic interpretation, but they're a lot more concrete to work with. And so our simplicial sets, for people who don't know, they're going to be these objects constructed by gluing together n simplices, so points, lines, triangles, tetrahedra, etc., together on their faces. And we're going to define the simplicial sets to be contravariant functors or presheafs from a certain indexing category to the category of sets. And we denote that delta, or the simplex category, and that is the category of finite ordinals and order-preserving maps. So the objects we're going to denote by n in brackets, and in the finite ordinal sense, that would just be 0, 1, 2, 3, until n. So for our presheaf here, we assign to each of these the set of n simplices, but the morphisms in this category, the order-preserving maps is the definition, but I think more clearly it's generated by two classes of non-identity morphisms. So you have face maps, which take an n simplex and map it to a lower dimensional simplex by leaving out the ith vertex. And we have degeneracy maps, which include one simplex include an n simplex into an n plus one simplex by repeating a vertex. So you kind of get a trivial higher dimensional simplex, or like a flat one. And so these morphisms generate all of the morphisms in this category just with compositions. And so a nice example of this is if we have a space X, we can kind of probe it and test it with maps out of the standard topological n simplices. And we can take all these maps and define that to be the set of our abstract simplices. And so this assembles into a simplicial set. It's called the singular complex of X. And we can also take a simplicial set and take all these abstract simplices to the topological ones. And this is going to be the left adjoint to singular complex. And the co-unit is a weak homotopy equivalent. So up to weak homotopy types, these things just correspond, which is quite nice. So this is pretty nice from a homotopy theory viewpoint, but we're going to want to have categorical interpretations in the sense of compositions and identities and such. And we're going to get these by like asserting that certain collections of faces also have a corresponding higher simplex. In kind of our sense that higher homotopies encode equality between things, higher simplices here are going to be our equality operations, I guess, for things like composition identity. So for composition, we can take, here's just the one simplex case, but we can take a sequence of one morphism. So we have F and G, and what we want to do is require that a morphism exists here, H, to fill in this diagram, but we also want a two simplex or a two morphism that like witnesses or encodes this higher homotopy between these. And in kind of our topological example and in general, we don't necessarily need this two morphism here to be unique. We can have multiple higher homotopies relating FG and its composition. So in general, this won't be unique. For identity morphisms, these degeneracy maps actually encode this. So we can duplicate a vertex, and that's that can be seen as saying we take a map and we stick an identity morphism somewhere, and then there's an identity 2 morphism, which is our homotopy with the original map. Any questions on that so far? Okay. So we have composition and identity kind of with these conditions, and we also want to talk about inverses. And so this just turned out to be asking for another one of these diagrams to kind of like have a third edge in a two simplex. And so if we have these two morphisms that share a target, we can encode the existence of an inverse to the upper one by just asserting that there exists this map F here and this like kind of witness or homotopy 2 simplex, which once more kind of captures the equality between them in a higher homotopy. And explicitly, sometimes we will define this F map here. You can basically go along H and then go back along the inverse to G, and that's our map F, if G has an inverse. And so, to capture these properties for all the n morphisms, for any n in I between 0 and n, we're going to define something called the ith horn. And that is going to be these collections of n-1 simplices that are obtained by deleting the face opposite the ith vertex and the interior from the standard n simplex. And so that's a bit unwieldy, but if we go back to this one, for example, just ABC in the morphisms G and H, that would be the second horn, or wait. Yes, that would be the second horn of the standard 2 simplex. C is our second object in our like 0, 1, 2 encoding, and so we basically delete this F morphism and we delete the face and we just get G and H. And so asking for inverses in that case is akin to asking that that diagram have an extension to a standard simplex. And we also want to consider the cases where we exclude I equals 0 and I equals n. So we don't consider the horns where we've deleted faces opposite the 0th vertex and the last vertex. And we call those the inner horns. And so this leads us, hopefully somewhat motivated, to the con-filling condition, which is also the condition to be an infinity groupoid. So a simplicial set obeys this if kind of for any map of these horns into the simplicial set, there's an extension along the inclusion into the standard n simplex. So we're asking that for any one of those little triangular diagrams of the form previously with kind of two legs of morphisms, there's a third morphism that commutes, and there's the two morphism that fills it in. And we want this for all n, so tetrahedra and that sort of thing. And so we say that an infinity zero category or an infinity groupoid is actually just defined by a simplicial set which obeys this condition. And as we'd hope, all of our singular complex sets are infinity groupoids. Any questions about that part? Okay. Great. So a big thing is we're going to want to model categories which have morphisms that don't have inverses. And so in order to do this, we actually really just need to drop this condition that these horns where I equals 0 or I equals n be filled. And this is going to be called the weak con condition or the inner horn filling condition. I believe Lurie mostly takes weak con condition, and I had to swap everything in the slides. But so this really just corresponds to excluding the diagram we saw earlier, which forces inverses. And then there's a similar diagram which would basically assert every other morphism kind of factors through every other morphism. And so this leads us as well to our definition of an infinity one category in a quasi-category sense. So we're going to define this to be a simplicial set obeying the weak con condition. So for any of these horns where I is not 0 or n, there's going to exist a map making the diagram commute. So we have a map which is an extension along the inclusion into the standard n simplex again. And so we have a pretty nice way to make infinity groupoids from a topological space, but so far we don't really have a way to make an infinity category yet. So one of the most standard kind of canonical examples is we can take a one category and we can define the nerve of it. So we have zero simplexes, or points are just going to be objects of C. Our one simplices are going to be morphisms. And in general, our n simplices are going to be sequences of composable morphisms. So, object morphism, object morphism. And so our face maps, which reduce the dimension of our simplices, so they kind of remove a vertex, they're going to be given by composing successive morphisms. So we remove whatever middle object was there and just have the morphism from composition. In our degeneracy maps, which kind of duplicate a vertex or an object, we're just going to insert an identity morphism in between our two little identical objects. And so this defines an infinity category which it obeys the weak con condition, so it's an infinity category, but it also does so uniquely. And not everyone will do that, but there is only one of these extension maps which kind of witnesses these compositions and similar. So the nerve is fairly nice in this, in that like you don't have choices of higher homotopies. Does anyone have any questions about that one? Oh, I should mention the face maps are given by composing two successive morphisms, unless you take a face map on an n-simplex and it's d0 or dn, then you just drop either the first or last object. So if you don't have a morphism on the other side to compose with, you just drop the object. And so we have a nice way to go from a one category to an infinity category, and it turns out there's also a pretty nice way to go from an infinity category to a one category, and a little unfortunately we do kind of, at least for now, have to go by the topological category definition again, which I know I said was bad to work with, but it turns out to have a really nice concept of a homotopy category, because we're just enriched over a nice category of spaces. We can define our homotopy category to have the same objects, and for morphisms we just take the connected components of our space, so you only care about the homotopy class of morphisms. And this actually turns out to capture a bunch of the information of our category. It's a really nice definition, but we kind of want to be able to use this with our nice simplicial stuff. So we're going to talk about some, I guess, like relations between a couple models. And in HTT itself, Jacob Lurie, there's a specific section which he says is just kind of a bunch of details and you can skip ahead. And so I will not go over like one big construction in that, but otherwise mostly we're going to get through all of that. So in addition to the quasi-category models we've been talking about with simplicial sets and the topological models, we can also define an infinity category to be a category enriched over simplicial sets rather than a simplicial set itself. And in HTT, these are referred to as simplicial categories, and that's usually what you'll find elsewhere. And so a really immediate thing, because of our singular complex and geometric realization adjunction, we have an equivalence between topological categories and simplicial categories. So this is really nice. And so we define the homotopy category of a simplicial category to be given by passing to the topological categories, kind of in this adjunction. And so the really natural thing that we're going to want here, and I guess a bit of background. So for the simplicial categories and the topological categories, there's a way of kind of taking a nerve of it and getting a simplicial set, kind of something we might want to be an infinity category out again. And so for the simplicial category, we can define this variant of the ordinary nerve, where instead of just taking composable sequences of morphisms, we kind of also descend into the simplices that are already there in our Hom spaces. And so it turns out for a simplicial category, if for all the objects our Hom spaces are Kohn complexes or infinity groupoids, so they're not just any simplicial set, but they are infinity groupoids, then taking this simplicial nerve is an infinity category in our quasi-category sense, and everything turns out to be really nice. And that is all for today. Anyone have any questions?
I haven't seen the hours release, and I haven't seen the Austin release.
Can't believe they heard that. Thank you. Yeah. To be more specific, 1.1.5 is the chapter where Lurie kind of does some constructions on simplicial sets and not simplicial sets, sorry, simplicial categories. He defines the simplicial nerve functor. It's just kind of a fairly combinatoric bashing out definition, so I did not want to include it in the slides, but I think it's worth reading because it does set up the it does kind of set up these equivalences, and using these equivalences, we do actually we get like, so every, I don't know, the big one is probably remark 1.1.5.18. So every simplicial set is kind of categorically speaking equivalent to an infinity category, which is really nice. Every simplicial set is also categorically equivalent to, we take like 3 of kind of the adjoint functors and compose them together, and you get the like topological nerve of a topological category constructed from the simplex, but it turns out to be equivalent to it, so you have a kind of this construction of it as well. I don't know exactly like how much you might need this going forward, but especially if you're coming at a second pass, it might be a useful reading thing. As for, I know there was exercises mentioned the last time as well. I think a pretty good one is proving that the singular complex is an infinity groupoid explicitly. Or, I mean, if you have any other examples of infinity categories you're interested in, it can be good to just kind of write down and follow through the weak con condition. Yeah. Thank you so much for coming.